Okay, so I just want to reiterate that a federated learning network is a mathematical model and it can be chosen. So you, as the machine learning or federated learning scientist or engineer, you choose, for example, the edges. Often you can choose to some degree which nodes you connect by an edge. You can also often choose what model you use. I mean, this is then model selection. The, the, the job of a machine learning engineer is often to select, to choose the right type of model. And this is only one design choice for a federated learning network. We have the design choice. Also, first of all, which devices do we include in the network? So we could use all devices that can be reached from my current MacBook via internet connections. This is a very large network, or I could say all the devices within my flat form the federated learning network. Also, this is already a design decision. So which nodes to include, or which devices to include, which are represented by nodes. Then the local models for each of the nodes. And for these design choices, we typically need to take into account the physical identity of the corresponding device. Like if a node represents a small embedded system, then we might not use as local model a large language model that cannot be ever trained on that small device or even stored. So we might only use then a decision tree. So the practice should guide the choice for the model in order to minimize the modeling error, as I mentioned before. But within this course, the main design decision that we will be worried about is the edges. So I will then later in this session talk about ways to choose to make good choices for the edges. So which devices should be connected within a federated learning network. And all these design choices determine or influence the computational and statistical properties of federated learning algorithms. So this will be a main theme of the remaining lectures to study how does the computational complexity change if we use different choices for local models or edges, and how do the statistical properties change then? And typically there are trade-offs. So when you want more accuracy, so you want to have a federated learning system that trains very accurate models, then you might typically need more computation or communication across the links between the nodes. But there's also trade-offs between other properties like the robustness. We want federated learning systems to be robust against different forms of perturbations, intentional or unintentional. We want them to be explainable, and we want, of course, a key characteristic of federated learning methods is that they allow for some level of privacy protection. But typically, we have to trade off privacy protection with computational complexity or accuracy. Yeah, I just want to visualize this design space and how they map to objectives. So we have this design space. As a federated learning designer or federated learning engineer, you can choose the edges. You can choose to some degree which devices you connect, devices you want to communicate with each other and collaborate on the model training. You can also choose what type of models you want to train. So this is, of course, a key topic in machine learning research, how to find what are the right type of models for a given application. And these design choices then map to the objectives, performance objectives, like the accuracy. We want, of course, to have trained models that are very accurate, have a very small test set error, for example. But they also should minimize the compute time. The more computation federated learning algorithm needs, the more resources are needed, electricity, and also monetary costs if cloud computing is involved in a federated learning system. Okay.